Okay, we're very happy to have Sujay to tell us about SCFT and the VOA correspondence.
Thank you. I'm very happy to be here. I'm grateful for this.
我们这次这个 is the new program in our group. We will welcome Sujay. We are here.
Hi everyone again. So today I want to talk about, as the title says, the SCFT VOA correspondence for twisted class S. There's a lot of adjectives in that title, but I'll go through them as we go along. So this has been work that I've been doing with my supervisor over the last, during my PhD, and I think it's pretty interesting with this sort of stuff I'm interested in, mostly to do with vertex algebras and mostly to do with vertex algebras coming from 4D theories. I'll go over that in a second. So I think vertex algebras probably are a little bit niche, so before we start, I'll go over a brief review of what they are. I'll go through an example. Then I'll talk about how this correspondence works, and in particular apply it to the theories of class S. I'll then go over a really nice construction of these vertex algebras, coming purely sort of making no contact with physics due to Arakawa. And that will raise some puzzles, which I'll partially answer when I go over the construction of the vertex algebras for twisted class S. So in this setting of twisted class S, you incorporate non-symmetries. So to start with, I should define a vertex algebra, and this is kind of a painful definition, so bear with me. But a vertex algebra is a tuple B at 0, del on the map Y, where V is a vector space. I'm just working obviously throughout, so it's a complex vector space. This 0 is the vacuum. It's a distinguished vector in my vector space. Call it vacuum. And somehow it's kind of the building block for the rest of the vector space. I have this operator del, which is a linear map on the vector space, and I'll call it the translation map. And finally, I have the most interesting structure, which is the Y, which is a map from the space V, which are also called the space of states, into, well, operators on V and V, valued, so it lands in Laurent series in some Z, whose coefficients are endomorphisms of V. So there's some axioms that all of this data has to satisfy, but for now, I'm going to just say a little bit of notation. If I have some A, some vector in B, I'm going to write a Z to be Y by Z. And because this is a Laurent series, it has a Fourier expansion, and I can write it as A subscript n, Z to the minus n minus 1. And n runs over all integers. So somehow this gadget is meant to account for the sort of algebraic data of a 2D polymorphic CFT. I won't really have time to go over that, but a lot of the features of a 2D CFT are present here. The states, the vacuum, and this Y is the operator state correspondence. Okay, so I have all of this data. I also have some axioms that I need all of this to satisfy. I'll squish them all at the end because they're not super interesting. I should mention them. So, axiom 1, if I take y and I apply it to my distinguished vacuum vector, then I just get the identity on V with no coefficient of z. If I take any of these AZs, which are called fields, and I act on the vacuum of them, then I just get A plus terms that are vanishing as z goes to 0. So you can kind of think of this as this is a field, and inserting it creates a state A. I want that my translation operator acts like a derivative, namely, if I apply it to z, I get a sort of formal derivative acting on the field. I want my vacuum to be invariant under translation, so this del kills my vacuum. And then finally, I have the most complicated property, which I'll write as a star, and this one's called locality, and it sort of governs how bad the how close to commuting two arbitrary fields are. So if I have some two vectors AB, then I can form two fields, AZ and BW, and I can ask for their commutator. And I require that this is regular if I multiply this by some z minus w to the n, to some big N. Now, this condition is kind of confusing because it just sounds like I'm requiring AZ and BW to commute, right? If I multiply by some z minus wn, then it doesn't really work that. But no, but what's going on is that I have to make sense of these. So A of Z and B of W are both Laurent series in Z and W. And so to make sense of this, I have to pass to a ring which has both Z and W. And in that ring, Z minus W is a zero divisor. So just because Z minus W times this is 0 doesn't actually mean that this thing is 0. So this commutation relation is a bit weird. We can talk about it later, but roughly the way to think about it is it governs how badly the fields can get commuted. One of the consequences is if I try and expand AZ BW in powers of Z minus W, it's not going to go on forever in the negative Z minus W direction. Okay, so I mentioned that we can do this expansion, and in particular, the final thing I want to say about this. If I have a field AZ, I can ask for AZ, BW, and just like I mentioned, I can expand this in powers of Z minus W, and the coefficients of that are going to be these Fourier modes acting on my vector B. So, the knowledge of how all of these operators that appear in my map, my operator state correspondence, these Fourier modes AN have exact, they can all sort of be collapsed into the data of this thing, which is called the ODE. So a sort of pragmatic way of writing down a vertex algebra is to give me some set of states and tell me what the OPEs between them are. So if you specify those, I know what the ANs are, and also how the ANs act on every other state. And so I know the full data of everything. Okay, so that was a lot of data. I would like to now give an example, which is hopefully should set this before I do any questions. Yes.
Study these vertex algebras in like different contexts where maybe like when you do regular SCFT, you get these sort of poles, right? Sometimes some exotic theories you get like fractures and other things. Were there people thought that mathematical purpose?
Yeah, so yes, so some of this branch code stuff is related to how you should think about vertex algebras with odd, like fermionic states. You can look for mild generalizations of vertex algebras where you can have like logs appearing in the OP, which is kind of maybe what's most familiar. They appear in like free fields. And you can do that as well. For my purpose, I really want this slightly more strict definition. Okay, so I want to give an example, which is going to be useful for the rest of the talk, which is the universal affine vertex algebra BKG. So let me fix a Lie algebra G. So it's a simple Lie algebra. It doesn't have to be simple, but it just makes introducing it easier. And I'm going to pick a basis JA. A runs through 1 to some dimension G. And I'm only picking the basis, so it's easy to write down. Then, given this, I can define the affine Kac-Moody algebra G hat as the central extension. G hat is extension by one-dimensional K of the Beem algebra. And so, in particular, G hat as basis JA from the old basis, and now a subscript n, which is just my way of writing down the package JA. And I can write down all of the commutation relations of this Lie algebra in this basis, and they're reasonably concrete. So I take JAM, and I also leave bracket with JB n. This is going to be just the commutator in the ordinary Lie algebra of JA and JB times T to the n plus n. These just add, plus a sort of residue term m times JA, JB, and this is the coefficient of k. In particular, this JA, JB that appears here is some rescaling of the filling form by the dual constant. So every Lie algebra has a unique filling form. I then just take some rescaling of it, and that's what I mean by these brackets. This somewhat conventional, but okay. So now I have this like huge infinite dimensional Lie algebra, and G hat itself is not a vertex algebra, but there's a representation of G hat, which is. So, given this data, let me define VKG. So, VKG is defined to be the induced representation of G. So I start with this one-dimensional representation, which is spanned by just some one-dimensional vector space, and you pick the basis 0, het. And the properties are that this entire subalgebra of all of the positive powers of t, including 0, just annihilates 0. So G T 0 is 0. And this central extension acts by this number k that I picked. Okay. So this object, VKG, is the vector space V that appears, is an example of a vector space V that can appear in our definition of the vertex algebra. So claim VKG is 0 that I specified, dt, and y, which I'll fix right now, is a vertex algebra. So to fix y, it's again useful to pick some kind of a basis. So there's a map from G into VKG by taking one of my basis elements and putting it as x1, acting on the vacuum. And now all of the vector spaces, the entire vector space of VKG is like the span of all of the words that I can build in this way. I take like a bunch of these j, a, t minus 1s, and I like put them all together and I act on the vacuum. So all of the states look like. So j hat. And in particular, y takes one of these j hat a's and spits out some n, a, x1. So that's what the operator state correspondence does. And the clearest way to sort of establish what's going on here is to talk about the ODE. So if I take two of these fields, the ODE that I get is following. Plus so the only singular terms of the ODE are there's a quadratic pole, which is given by this like inner product between JA and JB. And then there's the usual commutation relation. Take the commutation of JA and JB and write down the hatted guy, and that's the field that appears in the symbol pole. And then there's a bunch of regular terms, which I'll neglect. So this this is the universal affine vertex algebra, and this affine vertex algebra knows a lot about the representation theory of this infinite dimensional G hat, but it somehow packages it in a different way by using this OPE. I want to introduce one more thing about VKG before I move on.
Question. So what role does taking the universal algebras play when you're doing this induced representation thing? Like, it seems like everything you wrote down on the right makes sense equally to write down if you didn't take universal algebras first.
It does. Yeah, that's true. That's a good question. Yeah, I think I can remove the universal signs. The thing that I'm a little bit worried about is issues about, so all of these like infinite dimensional Lie algebras, so really these are some like completions. So that's the only thing that could go wrong in terms of the induction. But effectively I don't think it matters, because you can write down every state very nicely with basis. Any other questions? Okay, so project. So throughout, I'm going to be interested in these affine vertex algebras with a special value of k, which is namely minus the total cost number. And this particular value of k, the level is special because at this level, this entire vertex algebra develops a large subalgebra ZG, which is a commutative vertex algebra. It's commutative in the sense that if I take the fields from this guy and I look at their OPEs, I don't get any singular poles. It's only regular terms. More importantly, this is not just commutative, it's central. It's the big in front of the center. That's to say that if I take the fields from this, they have non-singular OPEs with everything else inside VKG. So it turns out there's a nice result that you can write down set G very explicitly, and it turns out it's the polynomial ring in, so I runs from rank G. There's a polynomial ring in rank G many generators, but then you have like infinite series in each of them. And I want to introduce one more thing, which is Z, this holographic Z, which is going to be the center of the universal invertible algebra G hat, where I take the quotient by k plus check. And this thing also has a nice presentation. It's sort of the same as this, but now I have both positive and negative halves allowed. So this is maybe a lot to take in, but the sort of flavor of what I want to get across is that if I have a Lie algebra G, there's a canonical way I can associate to it a vertex algebra through this affine Kac-Moody Lie algebra. And at a particular level of k, a particular number k, this vertex algebra develops a large center, which is a special subalgebra inside it. Okay. Okay. Any questions? Move on.
Can you say again what is curly field?
So, one way of thinking about it is it's the center of the universal invertible algebra G hat when I push it out by the central ideal k equals a number.
Simplify.
Yeah.
Working modulo.
Yeah, another way of thinking about it, it's the Fourier modes of Zg. So I take all the Fourier modes of this vertex algebra, that gives me some big associative algebra, and that's also Z.
So it's generated by the certain G's or at the...
All higher Casimir's, that's the PI. So importantly, because you brought that up, I'll say it but without much explanation, V minus H check G, the critical level, is not conformal as an stress tensor. The usual Sugawara construction is singular.
Yeah, but what like we usually there is Hills as Arakawa,
Yes.
which is for the commutative
Yeah.
subalgebra because
Yes.
critical levels.
Yeah. Okay. So, alright, now I want to move on to talking about the SCFT VOA correspondence and where all of these things compare. So, okay, so now I want to change tacks a little bit and talk about how these vertex algebras come from physics. So they always kind of came from physics, but how these vertex algebras are related to physics in higher than 2 dimensions. So I'm going to now shift my attention to 4 dimensions. And there are these special quantum field theories in 4T, which are called n equals 2 SCFTs. So these are quantum field theories that have non-minimal supersymmetry, but they're also conformal field theories, and they both give you a much bigger symmetry algebra. And there's some work by authors from 2013. This is work of, I won't be able to fit everyone's names, but this is work of Beem, Beem-Lemos-Liendo-Peelaers-Rastelli-van, Rees, who found a correspondence where if you give me a 4D n equals 2 SCFT as an input, this theory admits a certain kind of polymorphic topological twist, as well as an omega background. So somehow I started with the 4D, and I made 2 of those directions topological. I made the remaining 2 into a complex C plane, and the omega background means that I can't move in this topological direction. Somehow I've taken my 4D theory and made it a 2D holomorphic one, and in a 2D holomorphic theory is more or less the data of a vertex algebra. So starting from a 4D n equals to SCFT, there's a canonical edge way to associate a vertex algebra. And in particular, this map knows a lot about the physics on the left. So what do I mean by that? So if I call my theory over here T, and I call the output vertex algebra LEV of T, then there's a nice like dictionary you can build up in this way. So first off, if my n equals 2 SCFT has a global symmetry with Lie algebra G, again, a kind of global symmetry, but the sort of abstract way to write it is that I have a map from this VK G into VT. And this is the map of vertex algebras. And this level K is fixed by 4-dimensional physics. So some 4D correlator will tell me what that K is, basically. So if my theory is sort of has an action of G, my vertex algebra becomes a module of VKG. Another nice fact is that 4D equals 2 SCFTs have Higgs branches, much like 3 equals 4. And on the vertex algebra side, I can recover this. There's a particular operation I can do starting from the vertex algebra, which takes the vertex algebra and gives me a Poisson variety at the end of it. I'm going to call it the associated variety of T. And this is a conjecture that the associated variety of this vertex algebra recovers Higgs, but it's a conjecture that's been checked in infinitely many examples. All of the examples I'll talk about today, this is known, so it's a pretty strong conjecture. And finally, although I'm making a very brief list here, if I have a theory with a global symmetry G, and I want to gauge that symmetry, so I want to gauge the G symmetry theory. On the vertex algebra side, it would be gauging the action of this VKG, which is kind of the RST gauging. But the sort of formal way of writing that is that you take semi-infinite cohomology. I'll say a little bit more about what that is with respect to essentially VKG at a particular level. So this is some fancy way of writing down here some cohomology. Another way to think about this is that on Higgs branches, if I wanted to gauge a symmetry G, I would do symplectic reduction with respect to G. And on vertex algebras, this semi-infinite cohomology is the kind of like vertex algebra analog of doing that symplectic reduction. In fact, in sort of the nice cases, this diagram commutes. If I have an M Higgs and I gauge G, that's the same as doing this semi-infinite cohomology of the vertex algebra and then taking associated variety. That diagram commutes.
So what does the notation mean? Like the three slots in the cohomology?
Right, great. Right, so this is relative semi-infinite cohomology. So semi-infinite cohomology is a cohomology theory for Lie algebras. The Lie algebra here is G hat. In particular, I care about modules at a particular level, so minus 2 H check. And this is relative semi-infinite cohomology, so it's chains relative to this G subalgebra. I can go into more detail, but writing down full chain because it's not illuminating. Yeah.
This fundamental supercontrol filter is doing what space? They're doing like platform, flat, up, or
so it's best to sort of think of this data, this VOA, as a little bit like not. Okay, so let me say it this way. I start off with R4, and I have C times R2. And I pick some plane, which is my C, and this vertex algebra lives on that. But it's best to not think about this too physically, because this vertex algebra is going to be a non-unitary 2D CFT for reasons.
So could you mention some topological concepts?
Yeah, so No. So that kind of topological test is when I'm compactifying, and I want to preserve a set of supercharges. This is when I want to like, it's related, this is where I want to like remove dependence on a direction. So this, I remove like a forced translation variance across two R directions.
And what is, there's some correspondence between the inverse of the CFT and
Yep, I'll add that in as well. So, yep, there's a particular limit to the superconformal index on the left, which is called the Shor index. Physically, this is the partition function on S3 times S1, where I pick some parameters for the 3 and 1, I squash them a little bit. And I get this back from taking the character of the vertex algebra. So vertex algebra also knows about the superformal as well. So what I want to convince you is that this vertex algebra knows a lot about affording n equals to SCFT. I'm sorry, that's a question.
So at least for rational SCFT, you can gauge multiple symmetries on the VOA side in the language of, I forget which direction the arrow goes, either the forward folding or simple furnish and something like this. But you're saying like gauging only how the symmetry here is really more some taking some homology here. Can you say something about that?
So very often when I want to do the description that you said, I'm gauging a sort of discrete global symmetry, or usually finite dimensional.
Right.
Here I'm like really sort of gauging by the action of an infinite dimensional group, roughly speaking. And that requires some like different technology, just to make sense of what it means to do this with infinite dimension.
Can you like reformulate gauging the discrete symmetries in this language? Do you think there's a nice way to do that? Or?
No, because I really need a non-zero Lie algebra, basically, to do this. But yeah, thank you, that's a good question.
And that's just the vacuum character, or there's some ways of getting other characters?
It's just a vacuum character. Yes?
Is there a way to get the Coulomb branch from the VOA?
So in 4D, the Coulomb branches aren't hugely interesting, mostly because, so this recovers the Higgs branch as a holomorphic, as a Poisson variety, so it doesn't know any hyperchaos structure. And in 4D, the Coulomb branch has no interesting structure that is not special Kähler. It's just going to be C to the rank. It's just going to be like affine, and it's going to have an interesting special Kähler structure, but that really won't be seen by this. And also, there's no way of like getting a Coulomb branch from this.
So maybe the related question is, if you compactify left side of the circle, there are some.
If I can classify what, sorry?
On the 4D guy on the circle, R1 cross R3.
Yes, yeah, so you can play the game, right, of course. So if I'm starting from a 4D n equals to SCFT, I can take a circle compactification to get a 3D n equals 4. I'll write it there. So 4D n equals 2. I can compactify on this one to get 3D n equals 4. And the Higgs branch is preserved under this compactification. So M Higgs just goes M Higgs. You can now start playing more elaborate games, which kind of comes up in what we'll talk about later, but I'll ignore it. But you can apply mirror symmetry and you can ask the questions of what kind of Coulomb branches will appear up there for these mirror theories. That's also a key question. Okay, so this vertex algebra knows a lot about the physics, but it's kind of a catch-22 in that to compute this vertex algebra, I kind of just needed to know all of that information anyway, so we're no better off. But there's a special class of theories where this isn't the case, and I can work out the vertex algebras in an independent way, sort of extract the information I want without really making contact with the detailed knowledge of physics. So that's what I want to do now. So these are going to be the theories of class S. The S stands for 6. Sadly, it's true. And the reason for that is because all of these theories have a 6-dimensional origin. So in 6D, there's a sort of unique family of SCFTs of n equals 2.0 SCFTs. These are kind of like maximal SCFTs. You can't have more super informal symmetry than this, basically. And these are all labeled by a choice of Lie algebra G, which is simply list. That is to say, it's of A or D or eta. So, starting with this data, doing the following. I choose some Riemann surface, and the data that's involved there is the data of some genus. I can have some punctures. In the full glory of class S, these punctures have like additional labeling. I'll ignore that to simplify matters. Right now, I either have punctures or I don't. If you're familiar with the labeling, these are full punctures. But I'll ignore the characteristics for now. So I have some surface sigma GS with a choice tau. Tau is some point on the moduli space of Riemann surfaces of genus G and S punctures. So I picked a Riemann surface and I picked a choice of complex structure. And after doing this compactification and a suitable topological twist to make the supercharges divide, etc., I'm left with a 4D n=2 SCFT, which is parameterized. All of the information about the theory is completely fixed by the data of a Lie algebra, a Riemann surface, and this choice of complex structures. So this is.
To ask you, actually, you went down in dimension 3. Is there a way of getting some kind of good information of this sort of algebra, like how you divide it into one theory? Sure, it takes all this form. The question is,
So that construction is, so in class S, that construction is really when you sort of have like a cylinder with punch, like a sphere with 2 punches in it. That's what that construction is nicest.
oh no, I think in class S, this construction exists. In class S, it corresponds like exists.
Right.
And then it's true that you wouldn't make sense in an arbitrary surface, that's
Right.
but
Yeah. Yeah. I'm not.
I mean, I just wonder if anybody's worked out.
Yeah, I'm not sure. I don't know.
Do you think there'd be a well conversation to compute a vertex algebra? By just thinking of Newtonian theory with what whole power states about?
So.
Would it be a VOA or something?
I think it should be true, right? It exists.
Yeah. I don't know. I think it should exist. I might just be completely off the mark. I think there's this work of Nick Gardner, it's coming soon. And he has these like VOAs, which are not of the raviolos. He has a recent paper.
We're trying to do VOAs on the ravioli.
Oh, it's VOAs on the raviolo. Okay, it's not VOAs on towers. My bad.
No, I think it's on the ravioli. I mean, we should ask him. Not
Okay.
but
I don't. Yeah. I can't think of any works exactly like this at the top of my head, but I do agree. I mean, QVOAs are definitely studied, so I wonder. Morally, this has to be something like QVOA definitions of the 3D n=4 story. So I agree, but I don't know any major references. Okay, so right, these theories of class S. Right, so then 4D n=2 SCFTs, and in particular, they're nice because I can read off a lot of their properties from the data of this surface. So,
That more done.
okay.
oh, like something that never be seen again.
Yeah, I should have put the fancy algebra stuff there. It's like, that definition is not useful. In which case, I'll bring this back. Oh, that's a good point. I'm not sure how useful that is for the Zoom people though. Well, I already can't hear you. I'm just kidding. I'm not sure how. sure how much longer I can speak without just shouting. Okay, so very briefly, I just want to mention some properties of these theories, and then we'll talk about the vertex algebras associated to them. So, right. So the first thing is symmetries. Every time I have a each puncture adds a G global symmetry. This isn't an exhaustive list, but roughly each puncture contributes at least a G global symmetry to this. So whatever theory I get, I have a G global symmetry for each puncture. Another thing I have is there's a kind of Higgs. There's a kind of Higgs mechanism that takes me from theories which have more punctures to theories which have less punctures. So going from a theory on S punctures to S-1 punctures, you can do this by a kind of particular type of Higgs. And finally, the sort of nicest part about all of this is that there's a really nice gauging blowing relation. So if I take theories on the three-punctured sphere, and another copy of the three-punctured sphere, then as surfaces, these are just two arrow paths, and I can just glue them along puncture components, and I should get the four-punctured sphere. This is just a cartoon so far. If I just have surfaces in 2D, I can glue them along punctures. And it turns out that this has a nice interpretation in the physics, where I take this theory, I couple it to this theory, so freely, and then each of these theories has a G global symmetry coming from the punctures involved in the gluing, and I just gauge by that G global symmetry. That's maybe not the right notation, but gauge by G. Where now this G symmetry is acting diagonally. Okay, so somehow these theories of class S are special in that they have a kind of building block. Once I know what the three-punctured sphere is, everything else is sort of built up by taking copies of these three-punctured spheres and building them. Case gauging, much like the sort of 2D TQFT. Okay.
Classify which is a puncture, it's like using like a fusion.
So you can think of losing a puncture as either gluing on a cap, or taking whatever theory you have, coupling it to the theory associated to a cap, and then gauging. This is not so great because the theory associated to a cap is not a good theory. The other way to think about it is you can trigger a Higgs mechanism where you give one of the moment map operators in your theory a nilpotent valve, and that activates the Higgs mechanism.
Is that a picture?
There's a picture of the level of Higgs branches. That's
Okay, so then say again what you do.
yeah. So suppose the Higgs branch of this guy was. This doesn't happen.
What you're doing has to have some phrasing and level of vertex operator.
Oh, so the thing I said was in the physics world. In vertex operator, well, that's triple-cycle reduction, which is the thing that takes a current algebra and produces a W algebra. In particular, like the Higgsing picture is something like, if this is the Higgs branch of sigma GS, then I want to give a vev to some operator of the theory, so a P. So, and the way I do that is that it's a C2 mod Z2. It's not C2, this is some generic Higgs branch, has some strata. Let me take this as my other strata. And my space of equivalent vevs is like measured by a strata, which is a higher convention. So I pick something. This is one of the verbs I give. This is a verb I set.
No, just say it word for it. If you want to.
So I give one of my moment map operators a null moment map. So this theory has G-plane symmetry, so it has moment map operators coming from each of the symmetries. And I assign a null code to that. So I assign them equal to some null code element. And the resulting RG flow will take me from sigma GS to sigma GS minus 1. Yeah, we can draw a better diagram, which is not something else that you can draw. Okay, so
just making sure you're just picking a point. So your point like
yeah, so as an Higgs branch, I pick some point in the smaller strata, and my new Higgs branch is going to be a slice from the smaller strata to the new one.
Okay.
And then that's the procedure that takes me from sigma GS to sigma GS minus 1.
So that's our level of Higgs range.
Mm-hmm.
The level of the theories.
At the level of the theories, it's this procedure of giving a VEF to my moment map operators. Okay, so these are some of the nice properties of these theories of class S. They're all 4D n equals to SCFTs, which means that I can apply that map, and the result should be an interesting family of vertex algebras.
Just making sure, so your theories are sensitive to tau, to the complex structure of the surface?
Yeah, so my theories are sensitive to tau. I didn't mention exactly why, because I'm immediately going to neglect that. But, yeah, immediately going to neglect. The vertex algebras do not. So, statement number 1. For slightly technical reasons, I'm going to restrict to genus equals 0. We'll get back to that. So, suppose I have the sphere with S punctures, then this gives me a 4D equals to SCFT, and in particular it gives me a vertex algebra, which I'll call B, labeled by the Lie algebra G, and the number of punctures S. And this vertex algebra doesn't depend on my choice of complex structure. So it's purely topological.
So if you break things with you have a non-trivial.
Yep, so it doesn't depend on tau, but really the correct thing to say is that this thing is locally constant on the compactified modular space. So automorphisms of this guy, aka the symmetric group, acts on this. There's an action of like the symmetric group on S letters that acts on this guy naturally. Physically, this is the action of S duality. It's exactly what you said, it's the braiding of these punctures around.
But that's not the symmetric group. Braiding group or the symmetric?
The action of the braiding group factors through the symmetric group. Yeah, as a quotient.
Okay.
So yeah, like, so the mapping class group here is the braid group, but the quotient is through the sigma. They're okay, in higher genus, this isn't quotient, which is what I'm avoiding that for now. Okay.
So you're saying you have like one sheaf of these algebras on this modular space?
Yeah, like
It's locally constant.
it's locally constant, and really all I want to say is that like automorphisms of FGS act on my vertex algebra. Well, monodromies. So,
Sorry, like, this is like, it's coming from this world and this twist. This is like some incarnation of like indices on the page.
yeah. It's exactly that. The indices are basically counting the states in my space. So. Great.
Which question do you need to ask to get to the W algebra?
The W algebra is in
That's your vertex algebra.
as my vertex algebra. So they'll never appear as a algebra in class S. The way to get them is to look at these Argyros-Douglas theories. A lot of those Argyros-Douglas theories are slices.
Okay.
Sorry, W algebras. As for what theory? So all of the Argyros-Douglas theories that are associated with vertex algebras will be some non-potent orbit or a slice to a non-potent orbit in inside some G. I forget the exact dictionary that goes between which G, which slice, and the data of the Arakawa theory, but it's out there. It also depends on which way you want to think about Arakawa theories. But yeah, they do that. But in this setting, we'll never get, without nice sense of isomorphism, we'll never get to any. We will get something quite related though, so I'll mention that. So, right, so whenever I add a puncture, I added a G global symmetry to my theory. My dictionary says whenever I have a G global symmetry, I have an vertex algebra analog of that. And in fact, every time I have a puncture, I have a map from the critical level, so the special level where I have a center, into VGS. And because these are all global symmetries that commute, the images of these maps are all commuting vertex algebras. Remember that a commuting vertex algebra is one where I have no singular OPEs. So I have one of these for every puncture. I'll mention it because it's useful, but I had this like Higgs procedure that took me from S to S minus 1 in vertex algebra language. That's written as I have an operation which is called Drinfeld-Sokolov reduction. It's a special kind of cohomology. And what that does is it just reduces the number of punctures by 1. I won't really explain exactly what this function is, but I have an operation that reduces the number of punctures by 1. So somehow, if I have it construct VGS, I can construct everything before it by just formally applying Drinfeld-Sokolov reduction. And now, finally, the most interesting property comes from this gluing operation. So, I have to rub it out. So, at the level of theories, when I take two surfaces and I glue them, that's gauging. I mentioned in my dictionary that gauging in action is the same as performing this semi-infinite cohomology. So, I have this nice relation in this like family of vertex algebras, which are labeled by punctures, which says that if I start with a VGS and I glue to it some VGS prime, which I mean take the semi-infinite cohomology with respect to G hat G then this should obey the nice cartoon I have, and in particular, if I take surfaces with S and S prime punctures, I should get a surface with S plus S prime minus 2 punctures. So this is like my wish list of the properties I want from this family of vertex algebras, and I just want to say that like all of these are fairly non-trivial. There's also some like vertex algebra, some slightly more niche vertex algebra properties that I haven't said exactly to find them. But even just these ones are quite non-trivial. Here I'm asking it for it to be a certain kind of like module over the critical level affine Kac-Moody algebra. Here I'm asking for this like relation under a specific type of cohomology. Here I'm asking for some like horrible theory, like cohomology theory, to like link the various types of vertex algebras. So these are fairly stringent conditions on this family. And it turns out like that's enough to just construct it. It's constructed without any like sort of knowledge of physics. And that's what I will do next. But are there any questions?
Someone knows the answer to me.
Sorry?
The construction.
The construction
You
is
say it's stringent, but do you know if that's the only thing?
Oh, I don't know if the construction is unique, I know the output is unique.
Yeah.
Yeah, the output is, yeah. The resulting family of vertex algebras is unique. It's the unique family of vertex algebras that obeys this reduction, this relation. Yes. Was that your question?
Yeah, there's a question. So if you give me a state in your VOA or a vertex algebra operator in the VOA, should I think back in the 60s or something supported on some defect? Or what is it? How should I think about it?
Yeah, this is a picture that we had in our paper, in Chris. And the idea was this SCFT VOA story works all the way up at 60 as well, and that, the thing which is assigned to a 60 theory, is a principal W algebra. So in SL2, this is the Verasoro algebra at some specific central charge. But it's some vertex algebra, anyway. And you can try and think of what you could do by integrating it along cycles of this Riemann surface. And at the level of like indices, like at the level of like associated graders, this seems to work out, the counting matches. But we don't know, as of yet, of like a fully refined enough theory to like take actual operators of a VOA and use actual operators of another VOA.
I think I'm asking a much more naive question. I was thinking like, if you VOA is like you consider some operator sitting at the points and you can collect the points, and back in the physical world, what am I collecting?
Oh, in 4D, right. So I gave this story of the holomorphic topological twist. Another way to think about this, which is another construction, is I pick out some plane in my R4. I restrict so that all of the operators of my 4D theory only live on that plane, just by hand.
So that plane was that complex
It's
plane.
just for now it's an R2. I just picked a plane in my R4, and I get a 2D SCFT now by just restricting to live on that plane. So now I just have all the local operators I did before, but they live on the plane. And now I can play a game where I enforce a holomorphic twist on that. So my operators are the things that live in that topology. They're really like some descendants of local operators of the 4D theory.
Do you need it?
I have some like random algebras.
Sure.
What if you put extended operators?
Yeah, there's a nice paper by Juris, Weaver, I want to say Lotito, I think those are the three names, where they consider this. Somehow their picture really requires them to work in the Lorentzian signature, which bothers me.
Okay, that's kind of weird.
I think it's just really about like the kinds of like extended operators that should survive this chronology. Somehow they seem to exist in like Lorentzian signature. Something about superconformal algebra and representations. That story seems like really quite painful. Like,
I was just wondering if it was something simple.
But it's
if you do like a codimension 4 defect in the 2-0 theory on the ratchet plane, it transfers to a plane or something.
oh, right, yeah. So there's a story for that in like 60, quite nicely. And it's roughly that like these codimension 4 defects will be like EKG, which is saying that's example. There's of course another 4D type story where you can think about various types of geometries in 4D and how they could intersect with the big plane. Right, that's a little bit. Okay, any more questions?
Can you say again, what do you need to do to get the result?
Get Verasoro. So in this construction, Verasoro appears in 4D at specific levels for some of these Arakawa theories. It's not like SL2 type thing. Or you can go to 60, and then there's another version of this story where you assign vertex algebras to 60 and equals 2.0 SCFTs. And for a theory of type G, you assign the principal W algebra of type G at a particular level. I don't know.
So this is the level that that's dependent on the megapattern?
Oh, no. I think it really depends on the algebra G. It's some like special level for G.
How does this correspondence come to the genetic response where the level, like the central charge is the
So somehow this is like the other side. So in AGT, you're on the surface and you've already compactified the 4D. Here I'm like on the 4D and I've compactified it 2D.
So you switch the two Riemann surfaces, the one which is the 6D compactification and the other is half of the 4D surface.
And here I don't have like any parameters that are swishing. Like this Riemann surface, the vertex algebra doesn't have any swishing to it. So. Okay, so I want to now talk about the construction of these vertex algebras.
Actually, can you say how slowly
Right. So in AGT, you start with the 60 theory, and you pick some M4 times a Riemann surface, and then really the whole AGT story works because the vertex algebras, these W algebras that you get in that story, are where you compactify this guy. But somehow that W algebra really lives in this sigma. It's a 2D CFT on this set, honestly. This vertex algebra really lives inside this M4. I've compactified on this sigma and I've picked out some auxiliary Riemann surfaces like this M4. That's where all of my vertex algebras live.
You're not able to change the sigma and
No, because I really compactified on sigma.
And the twist in the 60s, they're really asymmetric. Like in AGT, you're going to control flux, so you know that's the hall in the direction. Whereas here, the only sense in which it's all work is the something just a lower.
Yeah, morally it's like really topological in the same direction, but polymorphic in the same direction. Okay, so I'm going to write examples, but I'll do that at the end. So let me just go on to construction of these. And this is due to Arakawa, and I'll talk about an extension of this at the end. So everything's been nice and pictorial so far, so the construction should be as well. And the picture we're going to have in our heads is if I have some Riemann surface with S punctures, at least at the level of the cartoons, I can pretend that I have a construction where I take a cap, I take another Riemann surface, and instead of gluing along boundary components, I just pretend I can glue along interior components. And this would like undo, basically, it would undo true philosophical reduction, it would just add punctures. So if I knew what the cap was, and if I knew what this interior gluing was, I've fixed G to 0. I just repeatedly do this entire interior gluing. And
it can't stop some question. It's somewhat essential, but it's really, it's formal symmetry is essential, right?
yes,
You can't say,
you can't do the omega definitions. Otherwise, you end up with a soft vertex algebra, which doesn't have any easy. So, right, so I'm going to do this construction in math, and so what I need to do is I need to tell you what this cap is. I need to somehow uniquely specify it, and I need to tell you how to do this interior gluing. So let me do that. So the cap and the cylinder. So it turns out that there's like enough sort of constraints that the cylinder is really already fixed. And why is that? Well, if I have some kind of Riemann surface, and I glue onto it a cylinder, this is just normal gluing along boundary components, this is just the identity operation, right? Like this thing is still the same topological Riemann surface. 1, 2, 3, 4, 1. Doesn't change it. What that means is, if I started off with any of my BGS's, and I glued BG2 via this prescription of semi-infinite homology, this is the identity. And this is a really stringent requirement, and this work of Kac-Moody and Kidscory, which tells us that there's really only one thing that does this, that has this nice chronological property and the semi-infinite homology. And that is BG2 must be the chiral differential operators on G. Now, maybe after the talk I can explain more about a concrete version of how to think about this. But for now, this is some like well-known vertex algebra. And moreover, it's like uniquely fixed by requiring that gluing this under semi-infinite homology acts as the identity. This is like a unique object that does this. Now, this was the cylinder, it wasn't the cap. But remember that I had like a nice way where if I have n punctures, I can get something with n-1 punctures by performing Drinfeld-Sokolov reduction, which is no longer. But I'm going to appeal to that, and I'm going to define VG1 to be the Drinfeld-Sokolov reduction of CD over on G. For historical reasons, I'm just going to call this WG. This thing is called the equivariant affine slowly slice, or the equivariant affine W algebra. The reason is because if I pass this through my associated variety picture, the thing that I get is the group G, which is simply connected as the algebra of small g, times the slowly slice. So this is like some equivariant version of a W algebra. And in finite dimensions, this is a construction due to stuff. This is something that's symplectic. This is something that symplectic singularity people like. So okay, so I've now fixed the cap. It's this object WG. As a shameless self-promotion, let me continue the story and go to E0G, which
What do you say it's equivariant?
it's equivariant because it has a G, as a big G symmetry as well. So a normal W algebra has no G symmetries because it's somehow a slice between two orbits. This is a W algebra that has an actual G as well. Somehow what this thing will look like roughly is it looks like this thing will be, so this will be some module of the affine W algebra which also has a G symmetry. That's the sense of which is equivariant. We can go even further and reduce all of the functions. So this is the vertex algebra corresponding to a sphere, and this I'll call the chiral universal centralizer. And this is interesting because if I pass this through the associated variety, I get, very interestingly, I get the equivariant Borel homology of the Grassmannian homology spec. AKA, this is the Coulomb branch of field edge theory. So this is pretty interesting though.
So this is associated to sphere.
To sphere.
You're doing class test on the sphere with 0 functions.
Yeah.
So you took something horrible, you got something
Yeah. So in fact, all three of these objects, as physical theories, if I did the compactification on a cylinder or on a cap or on a sphere, they're not good SCFTs. They're not unitary. They don't have like a good spectrum, etc., etc. But as vertex algebras, they're actually quite nice and of a lot of interest to vertex algebra people. Yes.
So with this moving process, can we, with this interior moving process, with the exterior moving process, what we get all navigate this?
Yeah, we would.
Doesn't, well, in hierarchy, there are multiple concepts. You said that it depends on the tower.
No, these vertex algebras don't depend on the tower. They only depend on the topological data.
Was there some story that the Higgs branch would include or you need to do it on the full theory?
No, well, it depends on what you mean by the Higgs branch, at what level of derived structure you keep behind. So, for example, there's lots of theories whose Higgs branch is C2 mod Z2, but they differ because there's some data about whether the singular point is really a point or whether it's BZ2 or BZM, whether it remembers extra-visual gauge symmetry. And I think the sort of consensus is if you keep track of that level of algebraic data, it fixes the vertex algebra. At least for these vertex algebras that come from physics. But I don't think there's a proof of that statement. So essentially, if you worked at the Higgs branch as the level of a derived stack, then maybe it was vertex algebra. Okay, so I fixed the cap. I told you what that is. Now I need to tell you how to do my interior loading. And this, I'm going to call Fagan Frankel loading. It's also not there. So remember I said a while ago now that there's a special level where this V minus H check G, this affine current algebra, has a center, which is this fading frontal center. And now, this is kind of unmotivated, but the motivation is probably a talk in and of itself, so I'll just say the answer. It turns out that if I do the following operation, So I'll say what I've done. Again, I've used this semi-infinite homology. But here I'm not identifying the actions of V, K, G. But here I'm identifying the actions of this fading frontal center. So each of these has an action of V, K, G. And so in particular, that restricts to an action of the fading frontal center. And what the semi-infinite homology is doing is identifying those actions. It's identifying the diagonal action on these two parts. And it turns out, this is theorem of Arakawa, that if I do this particular gluing, if I do this particular semi-infinite homology, I get that cylinder. And in general, a nice result, which is that if I start with something in, which is a module over this G hat at the critical level. Moreover, I want it to be GO integrable, since it's the category O of these vertex algebras. I can get something that's a module over the fading frontal center by performing Schoenfeld-Sokolov reduction. And somehow this procedure gives me a way back, where starting from this, I can end up here by doing this equivalent. Now, I've written this really suggestively, so it looks like an equivalence. This category on the right is like huge, so sometimes this arrow doesn't quite land in here. This isn't an equivalence as written. It's an equivalence if you restrict to the image of this function.
What is the category on the left?
It's modules over G-hat mod. It's essentially B minus H check modules. But I insist on G, loop G equivariant objects.
Can you say again which geometrical physical statement like this? Or is this
Good question.
construct?
This construction doesn't have a great like physics interpretation. The sort of underpinnings of this, some work by Ginsberg and Kashtan on the more touch power, the Higgs branches of these Sicilian theories, the Coulomb-Roche Sicilian theories, or the more touch power varieties, where they had this kind of interior gluing procedure. From the maths point of view, all of this comes from geometric Satake. But from the physics point of view, it's a little bit odd. Like there's no clear physical prescription for why you should be able to do this. If you look at the Higgs branch of a theory in class S, you notice that all of the Casimirs and the moment map operators coming from each of the punctures, they're forced to be equal. So this thing makes sense. Like the output of it is kind of makes sense. But there's no physical like origins to that. But yeah, it's a great question, one that I don't know the answer to, and one that I would be interested in figuring out what the physics interpretation is. I'll also mention just one more thing, which is that this kind of weird thing that I've written, it's a sort of like vertex algebra analog of a slightly more familiar thing, which is the G equivariant quasi-coherent sheaves on G star. So representations of G which integrate all the other representations of big G. There is a similar sort of thing you can do there. But here it's an equivalence. So these are G modules. This is some finite dimensional version of Trim-Fox reduction. So it's reduction. And the thing I land on here is it's Z mod, but it's representations of the universal centralizer. And here it's an honest equivalence. This function here is some. It's well defined, but it's a Poisson analog of that. And so this is work of Rees. That also Ginsberg. Touchdown. And really this is secretly geometric syntactic. That thing on the right is like, this thing on the left is like G representations. That thing on the right is like, that thing
Geometric syntactic for what?
For G.
Just for G.
For G, yeah. There's secretly a G. So the thing on the right is like related to, it's related to the Arakawa one. And the universal centralized. But that's just a.
I mean, that code isn't all that fancy stuff.
No.
That stuff is much fancier stuff.
Yeah. I wanted to mention that, like, yeah.
When you say this is an analog, this is some kind of
It's some
affine
kind of like,
analog?
yeah, it's
Oh,
some kind of analog.
that-
That's what I wanted to say. And this thing is like not. This thing is much more. Okay, so I claim have my interior glowing.
Sorry, just to make sure I understand. I was following that picture so far, like this faking Franco gluing, but what's the relation with the new diagram you had before in the middle? What's the relation? Why do you mention this?
This thing.
Yeah, why do you mention this?
Right, I mentioned that thing because all of my VGSs live in this thing because I want them to have an action of V minus H check. But they also live in this thing because all of them are like Trim-Fox-Sokolov reductions of something. I have this relation that if I apply Trim-Fox-Sokolov reduction to this, I get S minus 1. So any S is a Trim-Fox-Sokolov reduction of S plus 1.
Okay, fine.
So all of them also live in here. But in fact, they live in the image of that functor of H0 ds. But this thing is an equivalence if I restrict to that category. If I restrict to the image of H0 ds. So I can invert H0 ds reduction.
So you're saying that the Z, which is a center, like ZG, right? The X by, you pick some point in your surface, is that your original surface? Because you see, when you forget a puncture, it's like you had
when I forget
a puncture from S plus 1 to S. Position of the forgotten puncture to give a point.
I don't forget the puncture. Okay. Those punctures are honestly like boundary components. They're not like really. I've been drawing them as like circles because they're really like boundary components as opposed to just punctures on the surface.
Okay.
Well, what I want to say is that it's not that I'm forgetting a puncture and really closing it off.
Okay.
So, in other words, my claim is that. Z G tensor S so I had a functor that takes this and produces this, which is Trim-Fox-Sokolov reduction.
Oh,
I inverted that.
Hiding and removing puncture.
Yep. I've just found an operation that like inverts that functor. And that's this. Okay. So in general, I can construct any of these VGSs by just repeatedly doing this. Because I know what the cap is, so I know what VG1 is, I can compute VGN by just repeatedly doing this. So formally, I've like constructed like some this thing. And really that's as far as we're going to get. I'm not going to write down generated relations for any of these. it doesn't go well.
And you're saying that it's embedding in one direction?
Yeah, so it's an embedding in that direction if I don't restrict. This category on the right is very, very big. Somehow, you notice that I have a geo equivariance here, but I don't have like any kind of equivariance thing there. That's kind of why it fails. Like this thing is too big. I'm asking for like Lie algebra modules, so I can ask for Lie algebra. But okay, so the construction is the following. I just take BGS to be repeatedly through these caps. I'll write that as a star. As many as I need. This, and that constructs BGS. It was shown by Arakawa that all of the other properties that I wanted from my theories of class S, which was that they play nicely under gluing, they do this thing which is possible reduction, and a bunch of properties that I didn't mention, including the characters, all properties follow. In particular, I'll say again, with this definition, it's true that if I compute these gluings, I indeed have this estimation.
And when you draw that picture, do you really honestly want to mean that we just added a smooth ball, or you should still think of as a cap attached to the?
I really added a smooth ball.
So that's really an equivalent over there.
A real equivalent. Yeah, this is really nice of you. Yeah.
So there's why there's like a effect of a smoothing, like it's like you're gluing these two guys, I don't know that you're smoothing this guy.
Yeah, geometrically this is like this is the kind of issue. Geometrically this like doesn't really it's no good. Like from a physics class S point of view, there should be no physics operation that like glues these two things in boundary components. So it's a bit.
I mean, does it work generally like just give you two Riemann surface at 2 points and like glue them together at a point and smooth the node?
Sure, you can do that at the level of surfaces, but this is like there's vertex algebras that are sort of associated to these surfaces, right? Whether it works for them.
You know, you're looking at some similar loci in the model space and then.
Oh no, I don't think that's no, because all of the singular loci in the moduli space look like decomposition into three spheres. Sorry, into three function spheres. The moduli space of an S-function sphere is a various like there isn't one. This is like
any degeneration will move through some similar loci, right?
The singular loci look like decompositions of the surface into its path decomposition. None of those paths decomposition have one where you just bubble off a sphere. That's not a complex structure. Singularity.
Yeah, but I'm not completely but if you take the Shor index of the genus G, aren't these QM must be
Yes, you are absolutely not misremembering it, that's correct.
Alright, okay. So now I know this right.
Yeah.
But there was an operation which was really, there were two different things.
Oh.
You add a smooth ball and a cap. Those things make sense. That was like whether a smooth union is like S0R, inverse S0R, and I mean basically, yeah, and the cap was like an S-band. So those things make sense. There was another operation.
Okay. Well, that's
Okay,
awesome.
so you can put in the simple.
Okay, so I have a little bit of time left, so I want to, shamefully none of this is my work, I was just reviewing instruction by someone else, so I'm trying to talk about what I've done. And to do that, I want to motivate something a little bit, which is that everything I've said was like super far too general. Like, at the very beginning of the story, the theories of class S required simply Lie algebra G, still down the top right. Everything so far was like too general. I could have chosen any simple G. And indeed, this construction of Arakawa, this like gluing and this incredible technique, it works for any simple G. In fact, it works for any semi-simple, but certainly for any simple G. There's no requirement that anything has to be simply fixed. So somehow this is like too general. And talking about how to interpret this construction for G non-simply laced is quite speculative. Instead, I want to answer a related question, which is that usually how you introduce non-simply laced symmetries in physics is you introduce these things called twisted functions. So now we want to talk about twisted class S. And so twisted class S is a refinement of the normal class S, where instead of just compactifying on a Riemann surface, that's a choice of complex structures, I compactify on a Riemann surface with a local system of Dingin diagrams. So essentially what that means is that not only do I have these normal punctures, I have these special punctures, which have these like branch cuts on them. So I can have punctures which are labeled by a choice of outer automorphism in G. So these white punctures are labeled by 1, and these punctures are labeled by some non-trivial outer automorphism. And what that means is that every time I have one of the normal punctures, I still have a G flavor symmetry. But now every time I have a red puncture, I get a G T flavor symmetry, where GT is the sigma invariant part of G up to a line equals 2. So, for examples, if G is of type D, and the twisted guy is Cn minus 1, it's A2n plus 1, then I get G n, and so on. So I can get all of the non-simply laced ones in this way, including F4 and G2.
So the first kind of automorphism, when you go around the special functions, what happens if you go like around the handle?
Yeah, so you can have, yeah. So really, if I have a genus non-zero surface, I should be very specific. I'm going to again cheat, get rid of all handles, so I can only have these, but absolutely you're correct. And that actually leads to an interesting S2
And you only want to put it on pair, for example, right?
Yeah, so it has to be, I can put as many as I want, but I'm going to say that sigma squared is equal to 1, it's order 2. So I need the, it's a local system, so the product of monotomies around 1 should be 1. So all of these twisted functions here has.
So they come in pair, and each pair are labeled at the same sigma?
Yes, it's order 2. There's only one non-trivial sigma. I'm gonna, essentially the order 2 restriction just means I'm not considering default. Like, I've already ignored I'm gonna ignore
And is there
default.
issue with it?
So it has an S3 outer automorphism.
Yeah, what's the problem there?
The Z3 twist is complicated. The construction that I'm going to propose just doesn't work with Z3 twist. I'll talk about why in a bit, but it's kind of technical. Yeah, so I'm ignoring G2, as it always is. So this now produces a new family of SCFTs, which are labeled by this twisted surface. So let me call this surface we call it CMN, and it has M untwisted G punctures. And now because the twisted ones come in pairs, it's just the most easiest to just remember. N is equal to 2n, and it has 2n GT punctures. And all of these are 40 equals to SCFTs, so I can associate vertex algebras to all of them. And in particular, I get a new family of vertex algebras, which are called Beem-N. And Now, every time I have an untwisted puncture, I have a map from B minus H check G. But now every time I have a twisted puncture, I have a map from B minus H check of the twisted guy, which is non-simply laced, into the MN. I also have the same kind of Higgsing relation I did before. I can close untwisted punctures using this like Higgsing relation. So H ds V MN is Dn minus 1 N. And then now finally, the most interesting one, I have like my gluing relations. So just like before, I have a untwisted gluing relation, where if I glue along untwisted boundaries, where I can glue along the untwisted boundary components, or I can glue along the twisted boundary components.
Like just one puncture or like the Kac?
Sorry, what, the twisted punctures?
Yeah, just like the twisted puncture.
I glue them
Here.
I glue them along puncture to puncture, not ends. So the picture is do like this. Along these two.
So is the pairing of the right punctures intrinsic, or is it just artificial?
It's purely artificial. There's going to be, again, it's a local system with an M, G, and N. Sorry, M. There's going to be an action of the braid group or a symmetric group which swaps all possible like branch cuts like before. So there's going to be an S4 on that surface that swaps all twisted punctures amongst themselves. The branch cuts are purely a figment of my imagination. They don't really exist. I draw them because it's easy. Okay, so I have this new family of vertex algebras which also incorporates these non-simply laced symmetries. And now the question is, how do I build them?
So what? You just have an odd number of this red puncture, does it make sense?
No. It has to be a local system of Jenkins diagrams, so the product of all the monotomies has to be 1. So because it's an order 2 monotony, it has to pair with some of them. There has to be a sigma and a sigma index every time. Okay. Now, I want to go about a construction that Chris and I proposed for these BMNs, which sort of follows the kind of techniques of Arakawa, but results in a new, quite interesting family of vertex algebras. I'm going to start with B11, it's a kind of mixed trinion. It's sort of the other building block. Now, somehow, again in this like very cartoon picture, this looks like if I took a cap and I took a cylinder and I like glued it together, again using this interior gluing technology, and Arakawa has already told me what all of these objects should be. This thing is what we've had so far, this WG that's entered into all of our constructions. This thing is going to be whatever Arakawa assigns to the non-simply laced GT. The construction follows for any G, so I can just ask, what is it assigned to the cylinder for GT? And it assigns the CQs on the GT. And I'm going to just write down the answer, but it seems kind of trivial. I'm sure you can get to a little bit more to show that it's not so sad. That's so our proposal is that this thing is exactly what you get by naively doing this work. Apply this calculus. Now, here, this is the untwisted thing in frontal center, and it's somehow acting on the twisted guy. There's a lot of sort of technology that I've swept under the rug that shows that this thing actually makes sense. There's an action of Z on everything. It's compatible in the ways that we want it to. All of that filters through machinery like OPAs and various like geometric stuff with OPAs. So if you're interested in that, we can talk about that later, but it's sort of super technical and not relevant.
So just make sure it's a GT, something above G-check.
It's not G-check. GT is the sigma invariant part of G.
Big lines.
And then take lines to.
Right, big lines to.
So GT is another way of saying it is GT is the simply connected group. Simply connected algebraic group, because the algebra is small GT. I always think simply connected. And so, okay, so this kind of proposal extends very nicely if I wanted to add more untwisted functions. I can just add more, and that gives me a family Beem-1, which I define as just taking, this is just shorthand for doing a bunch of these little intervals. Okay, so take M counts. Now, it turns out, for reasons that are to do with sort of the cohomological support of these various vertex algebras, this kind of Kac-Moody story breaks down if I wanted to introduce more twisted functions. So there's no nice way of constructing Beem-N. Having more than one pair of twisted functions, it doesn't work so well if I wanted to do it. You could think that the thing that you want to do is just to take one of these surfaces and glue in a twisted cylinder. That would like totally work. It turns out it's not correct. It just doesn't work. You can check this at the level of indices. It just doesn't give you the right answer.
Wait, you can't just do a
Yes, so that's exactly what we're going to do. Yeah, so instead we're going to go through the old definition, which is just that if I wanted to construct a surface with one extra pair of twisted functions, I can just glue in one of these chains. And this is just the ordinary gluing now. Right? So this gives me a sort of recursive definition of all of the VMNs by starting with something that is more untwisted functions, and then gluing along the untwisted boundary component one of these mixed chains. Okay? So this gives me a construction for all of the VMNs, and in particular, this construction is the unique construction. So I constructed them. One of the properties. So we're able to show that these behave as expected under kind of operations we want them. So, namely, this is a unique isomorphism statement. This family VMN that we constructed this way is the unique family of vertex algebras that have both these symmetries, and such that if I perform Dirichlet-Sokolov reduction, I reduce the number of functions. It's the unique vector isomorphism. it's unique once I fix a G. Every G is position variables. Something else you want to check is that the characters agree. Characters from physics were computed a while ago by Beem-Lemos-Liendo-Peelaers-Rastelli, and we managed to check that the characters of these things agree. And finally, the thing that you always want to check are these various gluing relations that we have. And that's the one, those are the hard ones to check. And what we've been able to prove is the partial gluing result. So if I have any surface Vmn, and I do a gluing where the other surface only has one characteristic punctures, then we're able to show that this works. So this is equal to m plus one, and moreover, just as well. So the reason we've been sort of forced to make this partial statement instead of the full family is mostly because of like how these actually work. When you do them, these semi-infinite cohomologies are in generically two-sided unbounded cohomologies. And so you have to perform some kind of spectral sequence argument and hope sometimes that it just collapses on page 2. And for all of these, it collapses on page 2. That said, this thing still lives in sort of, this thing is, these vertex algebras, which have more than one characteristic punctures, have support outside of cohomological degree 0. And that's kind of what makes it hard to introduce logistic punctures, and so it also makes it hard to glue them together. You have to work with bigger complexes. Bigger. So I'm running out of time. I'll just almost leave it here, but I want to just mention directions to head in, which is, so first is to honestly answer the question of what to do in the purely non-simple-based case, where not this slightly cheating of the twisted functions, just what is the physical interpretation of these class S theories where I just pick G to be non-simple-based. And somehow that's probably wrapped up in the story of 3D equals 4 vertex algebras. We'll talk about that later. And the final thing I want to mention is that these things all have associated varieties, and physically, these associated varieties should be Coulomb branches for 3D n equals 4 with non-cotangent type matter. So getting a sort of nice geometric syntactic style construction of these case branches, Coulomb branches, should be quite a nice result from the GRT programming. Leave it that.
Yeah, for sure. Yeah, sorry.
I thought you were going to tell us about this future.
I think I have 10 seconds left, so I don't think I should.
Not that strict.
Yeah.